You've probably noticed it at your local market. One week, the cost of tomatoes, onions, or rice seems perfectly stable. The next, prices double or even triple. Often, the immediate cause is right in front of us, a devastating regional drought, wiping out local harvests. For India, the stakes of those missing rains are immense. Nearly half of the country's entire workforce depends directly on agriculture, and the stability of the entire national food supply rests heavily upon the shoulders of the summer monsoon. But to know whether those vital monsoon rains will arrive on time, you can't just look up at the clouds over the subcontinent. Meteorologists predicting India's weather are actually analyzing data from a completely different part of the world. They are watching the vast Pacific Ocean, tracking a seemingly insignificant temperature shift of just 1 or 2 degrees Celsius, thousands of kilometers away. That tiny patch of slightly warm water off the coast of South America possesses the power to ruin harvests in Punjab, dry up reservoirs in Maharashtra, and double food prices across India. Let's look at exactly how this distant ocean anomaly controls the Indian monsoon. The climate of our planet operates on a rhythmic mechanical system known as the El Niño Southern Oscillation, or ENSO. You can think of it as a heartbeat that regulates global weather. This diagram illustrates the Pacific Ocean under normal conditions. Steady, powerful trade winds blow continuously from east to west, sweeping a massive pool of warm water westward toward Indonesia and Australia. As all that warm water pools in the west, it evaporates rapidly. This fuels immense storm clouds that deliver heavy, reliable rainfall over the western Pacific and surrounding regions. Meteorologists called this entire loop the Walker circulation. Back on the eastern side of the Pacific, near South America, the displaced surface water must be replaced. Cold water from the deep ocean is drawn up to the surface to fill the gap, a process known as upwelling. That cold water from the deep is packed with nutrients, creating an incredibly rich feeding ground that sustains Peru's massive coastal fishing industry. When this system runs smoothly, it acts as a giant atmospheric conveyor belt. The winds, the warm water, and the rain all work together to keep seasonal weather patterns stable and predictable across multiple continents. But every few years, that heartbeat becomes irregular. For reasons scientists are still studying, those powerful trade winds inexplicably lose their strength, or in extreme cases, stop entirely. This is El Niño. This map shows the immediate oceanic consequence. Without the steady wind holding it in place, that massive pool of warm water in the west slowly sloshes back toward South America. As it blankets the eastern Pacific, it acts like a lid, instantly shutting down the nutrient-rich cold upwelling. And because storm clouds form wherever the water is warmest, the rain migrates right along with it. The heavy precipitation abandons the western edge and shifts into the central Pacific and the coasts of the Americas, dragging the entire global weather system out of alignment. To see why this starves India of moisture, we have to look at how the summer monsoon is generated. As the Indian subcontinent heats up during the summer, the hot rising air creates a massive low-pressure vacuum, acting like a sponge, pulling in moisture-laden winds from the Indian Ocean. But during an El Niño event, that shifted Walker circulation hoards the cloud formation far to the east. The Indian low-pressure zone continues to pull, but the incoming monsoon winds lack their usual moisture and begin to sputter. This ocean temperature anomaly acts as a mechanical disruption, physically diverting rain away from the subcontinent and leaving India with dangerous dry spells and violently irregular storms. We can track the damage of this atmospheric shift through recent history. During the intense El Niño years of 2002, 2009, and 2015, seasonal rainfall in India dropped sharply below normal. In many districts, the production of essential staples like paddy and maize fell by over 10%. The toll on the fields is immediate. Farmers planting kharif crops like rice require heavily saturated soil to even begin sowing. A delayed monsoon shortens the growing season entirely, while unexpected dry spells later in the year can kill the plants right as they flower. The damage quickly works its way up the agricultural ladder. With less rain to grow vegetation, fodder for livestock becomes scarce, causing a drop in dairy production. At the same time, regional reservoirs fail to recharge, shrinking the supply of water for both drinking and irrigation. As harvests shrink, dairy output falls, and water resources deplete, the overall supply of food commodities plummets. Demand, however, remains exactly the same. That is the unbroken mathematical equation that causes food inflation at your grocery store. We have no way to stop ocean temperatures from rising or trade winds from slowing, but an El Niño declaration in the Pacific is no longer an automatic death sentence for Indian agriculture. Today, meteorologists use satellite arrays and supercomputers to forecast these disruptions months in advance. That early warning gives agricultural universities time to distribute drought-resistant crop varieties and allows farmers to transition to highly efficient systems like drip irrigation to stretch every drop of available water. Tracking this phenomenon maps the direct link between the Pacific's temperature, the atmosphere's circulation, and the stability of global economies. A single temperature shift in the Pacific dictates the livelihoods of farmers, the cost of living in urban centers, and the economic momentum of 1 billion people. It proves that in Earth's climate system, absolutely no nation exists in isolation.